This is Jeff Coronado at JCSE, and this is Bridging the Gap, an ongoing sequence used here at JCSE to bridge the gap for young structural engineers between where formal education leaves off and practice actually begins. So let me highlight for you. Down here is my email address. By all means, feel free to send me an email to clarify anything after this session is over, if there was anything that wasn't clear. But with that, let's go ahead and jump into this. It looks like we have a question that says, what type of loads, what type of loads do the different connectors transfer in the connection shown? So it's more of a conceptual issue, more of a conceptual understanding here that this young engineer is having trouble with. So we'll address what the different connectors here are doing. And we can pick out, and you know what, let's start off with, well, let's first show what we've got here. So here, this element here is a stud, okay? Here is our roof framing. So we've got a wood structural panel diaphragm across here and wood structural panel shear wall across here. All right, so we've got the stud assembly, the diaphragm, and it looks like here we've got a bracing element. All right, so that's a diagonal brace. So with that in mind, let's take a look here. So we've got a nailed connection. Looks like you can basically see the nails there. You have a nail connection between the brace and this block. So what direction is this brace going to bring a force in? Well, I think hopefully we can remember from junior level statics, you're going to have both a vertical component of force from that brace as well as a horizontal component from that brace. All right, so we know that this brace is introducing both vertical and horizontal forces into the block. Now, something that you will hear time and time again as a young engineer is you have to keep track of your load path. Loads have to be dissipated. You have to provide a complete load path for all of your loads. So in this case, this brace brings, well, let's start off with the vertical force. Brings in a vertical force. It's connected to the block. Well, where does that vertical force go? Well, likely going to go, once it's connected into this block, it likely needs to go into this roof joist as well as this one, right? So we do need to provide some kind of connection, whether it's nailed or hardware. We need to provide some kind of connection there to transfer a vertical force between that brace, or I should say between the block and the rafters. All right. Then we need to worry about that horizontal component that we saw, right? And that looks like it's being transferred from the brace into the block and then through this nail here that connects the block to the wood structural panel sheathing that goes across the roof. So it goes into our diaphragm, all right? So it looks like we have a load path there. Now, this connection, which means we've got right now, as it stands right now, we would be able to transfer the force from the brace into the diaphragm through this length of diaphragm. So the length of that block isn't a whole lot, right? That length of diaphragm may not be adequate to resist the entire horizontal force that the brace brings, right? The brace will bring in a certain amount of force. This amount of diaphragm will only be able to resist a certain amount of horizontal force. That could very well be what is going on with these elements here. Usually when you see elements like these, those are steel straps, and steel straps are good in tension. A steel strap's not real good at resisting compression. being a little facetious, it's not good at all, right? We have zero capacity in a steel strap resisting compression, light gauge steel strap. It's not going to be able to resist shear. So when you see a strap like this, it's resisting tension. So basically what we're trying to do here is share the load between what the brace induces into our roof assembly, how much shear the diaphragm is able to resist over this particular length, and then we're using straps. We're using this strap to kind of transfer some of the load that is in excess from this resistance right here, okay, over to the adjacent block where, again, we will have nails connecting the block into, or the diaphragm, I should say, the sheathing into the block. And likewise going in this direction. And it looks like we have another strap here. So we are able to massage the load from the brace through these straps into these blocks and ultimately into these nails to get that load to dissipate in the diaphragm. Typically, the way we look at these is we're able to dissipate the amount of load that we're able to dissipate in the diaphragm matches the diaphragm capacity. So it depends on our nailing pattern for the diaphragm. That's how much load we will be able to dissipate on a per foot basis. Okay, so it looks like to me, like, let me see, looks like with that we've addressed this brace, we've addressed these straps, and we've addressed these nails. Okay, let's now take a look at this connection here. Let me see if I can zoom in here a little bit. There we go. And let's look at this funky little shape here. All right, so this little gizmo is also an element intended to resist tension. It's basically being face nailed. We're not showing nails here, but it gets face nailed into the stud, and then it twists, it turns, and we're able to provide nailing downward through the diaphragm or into the diaphragm assembly through the plywood, I'm sorry, not plywood, through the wood structural panel and into the blocking below. So this element is resisting tension. Okay, well, let's see. So we've got tension, which means that element is able to resist some kind of tension that's trying to separate the stud assembly from the roof framing. And that would make sense. That's the kind of action that we have when we're looking at wind pressure perpendicular to the plane of the wall. It's going to create both what we would call a positive pressure, which in this case, clear this. In this case, positive pressure means when the wind pressure blows from left to right, and it causes the wall to kind of push into the structure. But more importantly, that tension element that we were looking at, this one right here, resists tension, which is what we need to do when the wall is being pushed to the left. So when the force pushes to the left, which is what we would call a suction force on the wall, a suction force or negative pressure, when the walls, there's negative pressure being exerted on the wall, it's going to want to split or separate the wall assembly from the roof framing. So we need something to connect those two assemblies so that they don't separate, so they don't pull apart. That's where we come in and put in this gizmo right here. And yes, gizmo is a technical word. Very technical, very sophisticated word. This little gizmo to prevent the separation there. me clear out here. Let me zoom out a little bit so that I can see kind of where we're at. Again, we always have to, as structural engineers, we always have to keep in mind all of the possible forces that our assemblies need to resist to make sure that we've provided the adequate load transfers. So we've looked at wind pressures perpendicular to the plane of the wall and looked at transferring that. We've looked at this brace and the X and Y forces that it induces. In terms of just vertical loading, well, let's see, vertical loading, we've got the stud, which is going to have a vertical load, and here it's cut, so we really don't know what's going on with the stud below. So we really can't check vertical loading of the stud in this detail. We would have to see what's going on below this to see if there's resistance for the studs, for the axial load of the studs. The connection that we have shown right here would be pretty inadequate, not completely impossible for it to resist the gravity loading of the stud, but it does look pretty inadequate. So I'm going to assume there is something going on down here that would give us the resistance that we need for the axial load of the studs. As far as the roof assembly is concerned, we've got rafters in there. Those rafters are going to need to be supported at each end of the rafters. So that's what I'm going to assume is taking the gravity load for the roof assembly. Excuse me. So there's one other thing that we haven't discussed, and sure enough, it's what's flagged out here with the cloud with number 1, which becomes kind of the crux, I think, of the question that the engineer had here. And there are 3 nails here. You can see 3 nails that we really haven't discussed yet. Well, let's see. What we have here is, now, again, if we look at our load paths, we've already considered the axial load, gravity load on the members. We've considered out-of-plane forces on the wall. What we haven't considered is the in-plane forces of the wall, of this assembly. The in-plane forces. So what we've got to consider is if we have this diaphragm assembly right here, right? If we have this diaphragm assembly, it's gonna induce a large force, which I'm gonna depict with a circle and a dot in the middle, meaning that it's a, well, you know what? Let me depict it. I don't know. Depict it with an X. The dot would mean the force is coming out of the plane, versus the X is a force going in the plane. Either way, it doesn't matter. It's reversible. We know that this is the in-plane force for the wall. The in-plane force of the diaphragm in this direction is due to either wind or seismic pressure. So so that's what causes the sheathing to act as a diaphragm, and that's a whole nother concept. So if you have a question on that, let me know. But that's what causes it to act as a diaphragm. So we've got the diaphragm assembly with a force acting into the plane, into our plane here of the screen. That force needs to be transferred out into the wood structural panel of our shear wall. So here's our diaphragm, here's our shear wall. We need to provide a load transfer that goes from the diaphragm into the shear wall for in-plane forces. Okay, so with that, what we've got here is this particular nail here is typically what we call a diaphragm boundary nail. And you will see that in the tabulated capacities for diaphragms. That's the diaphragm boundary nail. That's the one that occurs at the very edge of the diaphragm. So we've got a diaphragm boundary nail here that then we can think of as transferring the shear load that's in this diaphragm into whatever this element is. In this case, it looks like we have an end rafter or an end roof joist. So that diaphragm boundary nail transfers the shear load into that, end rafter. Then it looks like we have another nail here, which is clouded as number 1. So it's right here, this nail. So that nail now has to be sized. The nail, now the nail size is pretty standard. You've got wood structural panel and you've got lumber framing. You're going to see this connection be made typically with anything between an 8D to a 10D. And it basically depends on the load that, that you have there. But I would say more times than not, you're going to find yourself using a 10D to be able to transfer the forces between this diaphragm into this piece of lumber. Then the nail that we've got here, now this one connects 2 pieces of lumber. So typically to connect 2 pieces of lumber, we're going to use a 16D nail. All right, so this one is a 16D nail, but so the size may be pretty standard. What isn't standard is the spacing. We're going to have to determine based on the demand of the diaphragm, the load demand that we have on this connection, which is dependent on the load that's being transferred from the diaphragm through this nail, through the first nail that we looked at, the diaphragm boundary nail, into this 16D nail that we're looking at now. That connects these 2 pieces of wood. So basically we're transferring the shear from this last roof joist into this element here, which is a block. So to provide that shear transfer, we need to know what the demand is, what the shear demand is, and then determine the shear capacity of the 16D. And that way we can determine our demand capacity ratio for a certain spacing, or determine the spacing based on whatever demand capacity ratio we want to set, whether it's 1.0 or something somewhat less than that. But that's what will determine the spacing of that 16D. Once the load gets into this block, then you can see this nail here. This nail is what we typically call a shear wall edge nail. So that's our shear wall edge nail. Here's our WSP sheathing for our shear wall. This is our shear wall edge nail. So that will transfer the load from this block into the sheathing and then have it run down. And that completes our load path. All right, so that is basically all the connectors that are in this connection explained conceptually as far as what their purpose are. So for instance, there should be no misunderstanding. This, this element here, the gizmo, the gizmo that we talked about here, for instance, that is not going to transfer the in-plane force. If we have the diaphragm pushing out and our shear wall then pushes in to provide resistance, we're not going to be able to transfer the force between these 2 forces through this element. This element is not intended to take a load that would be basically perpendicular to itself. It's intended to take load, a tensile load, parallel to itself. It's basically a strap. You can pull on a strap, but you can't really try to shear it. You can't really fracture it perpendicular to its longitudinal direction. Nails, for instance, these nails right here, these nails are not going to resist that force. If we are looking to transfer a force like this, let's say the wind out of plane forces, we wouldn't be able to rely on these nails to do that. Why not? Well, because this nail would then be in withdrawal. So if I clear that out, I come in here. If I pull on this connection, if I pull here and I pull the wall assembly the other way, I'm just loading this nail in withdrawal, or this nail for that matter. Not really sure, probably both of them. Really loading these nails in withdrawal. All this nail has to do is pull out of the wood. A nail in withdrawal has a very low capacity. Yes, it has some negligible capacity according to the code, but it's very low. You're going to find that that once you do calculations on it, it basically doesn't transfer much load. So you're not really able to rely on nails for withdrawal loading. So the out-of-plane loading on the wall, you're not going to be able to transfer through those nails. And that's basically it. So that's this connection. Let me see, type of loads. Okay, so we discussed the loads, wind out of plane creating negative pressure, the in-plane diaphragm loading, the gravity loads. What type of loads do the different connectors transfer in the connection shown? So with that, we've answered the question. If you have any questions on anything that was covered here, by all means, send me an email and we'll try to get to it.